famine, pandemics, the threat of radiation, massive radiation exposure from something like a radiation reactor, explosion or something. And the new one is cyber attacks. So you can find out what we're doing about that by going to our website, which is called tosavetheworld.ca. And if you look at that, you'll find a lot of material. We've already been putting up bibliographies and videos about various aspects of this. And I'd like for you to be familiar with that and add your thoughts. You have places to have comments, discussions, and you can contribute. I hope there are people all over the world, crowds of people ready to hear our lecture tonight on Canadian snow and sea ice. Well, we have Canadian snow all around this building. Thank goodness there's no sea ice quite lapping up at our front door yet, but any day now, I expect that's going to happen. We get a tsunami of sea ice. Anyway, it's bad weather here today in Toronto, and nevertheless, some brave people have come out to share your thoughts with us and to ask questions when our speaker has finished explaining to us a little bit about his research. This is Professor Paul Kushner, who's in the physics department, a professor of physics here at University of Toronto. And part of a larger team he's been telling me about involving professors from a number of different universities and graduate students and so on who are working on the Arctic atmosphere and as well as, I suppose, the sea ice. So we're going to hear about that, and then he'll talk for an hour or so, I imagine, and then you can ask questions, and the people out there watching us from a distance can send us questions like comments, and he will answer them. So I'm not going to give your CV, but I think everybody's going to find out how exciting your background must have been. So, Paul Kushner.
All right. Good evening. Let's start with a sound check. Is it okay? Can they hear me out there? The microphone for the broadcast is right here.
That's correct.
Is that correct? Okay.
Yep.
All right. And
But just stand at the podium.
I'll stand at the podium.
Thank you.
Okay. So welcome. Thanks for coming out on a snowy evening. The irony is not lost on me that you get to actually experience Canadian snow on the very day I'm giving this lecture. Who would have thought? But it is February. We regularly have snow at this time. What I'll do today is kind of give an overview of my research, but I added something to the tentative title I gave you about the value of climate science. I'll add in sort of editorial remarks as I go, and maybe some of the discussion will head in that direction as well, because I know that this organization really tries to think of not just about the science, but why we do the science, and I think that's very important. So I'm a professor at the Department of Physics at the University of Toronto, and I come from a background in physics, but I had the good fortune actually to study here and get my PhD here in atmospheric physics, which most people don't know is a thing. But atmospheric physics is a field that focuses physics techniques, physical science techniques on understanding the atmosphere and more recently understanding climate and climate change. I also serve as the PI of a research network called the Canadian Sea Ice and Snow Evolution Network, CanSice. So you're going to hear a lot about CanSice, so I'll explain that as we go along. And that's a national research network. It's been a big endeavor, a big part of my life for the last 5 years. So I'm going to talk about that as well. So just to make sure that I get to my key points, I'd like to start with them, right? If we all have to leave for some reason at the beginning. And these are the key things I want to say today, and that is that just a broader point about climate science research, that it is really the scientific foundation for a lot of what we need to do to deal with the impacts of climate change and just climate variability as well. So there's a whole endeavor in environmental prediction, quantitative environmental prediction, which I'll explain about. And there's a lot of work to be done there. And so it's, I guess, a bit of a hack phrase to say that more research is needed. But I will say that more research is needed, and I'll try to explain why. And the kind of research we do in climate science, it deals a lot with uncertainty. So I'll try to give you some sense about the different types of, it's not just errors, but real true uncertainty that we deal with in our field. And to try to give you a sense of what our working life is like. And that within that, all that uncertainty, we still can make confident predictions. And I'm going to focus that part, and that'll be the sort of the meat of the talk, will be focused on the research in snow and sea ice, which I think is very exciting, and I like to bring to everybody's attention. And finally, at the end, I'll get back to this issue of how do we having hopefully convinced you or persuaded you to some extent that this research is worthwhile. I'll talk about the investments that Canada has made in this research, and you'll see that played out in the talk, and argue briefly that it's really worth supporting, but it requires some advocacy to do this. So you might have heard that climate science is settled. This is something we were talking about a couple of weeks ago. People say the science is settled. Why do we need more research? So I want to just sort of start from a really big picture perspective here and ask about the word settle. What does it mean to settle? Okay, so when people say that something is settled, I mean there's an argument between different parties and they've reached some sort of agreement, a common ground. All right. Another idea is that it's something that you've fixed. You've resolved it conclusively. There's no more to be said about a particular issue. So I just drew these from online dictionaries. So you can ask, well, what's settled in climate science? Right? What do we feel we really know, taking the latter definition? So what I'm going to do is not just parrot things that I made up. Right? I'm going to turn to assessments of climate science that have taken place over the last several years. These were commissioned by the United Nations through something called the Intergovernmental Panel on Climate Change. IPCC is the body that organizes assessments of research. So the IPCC doesn't carry out research, but they report on the status of research with investigators from around the world, researchers from around the world, and they put together these reports that have to be signed off on by nations around the world. And they produce these executive summaries. So these are big, thick reports in 3 parts. All right. I'm going to start by paraphrasing some of the main conclusions of the working group report from 2013. We're just about due for another one of these reports. But the 2013 assessment made some statements about global warming. Right? So what they said was that global warming is something that I'm going to run through the points here, the bullet points here, and then I'll talk about these graphs. That global warming is unequivocal and unprecedented. There's no ambiguity about it, and we haven't seen it before. It's driven by increased greenhouse gas concentrations, in particular carbon dioxide, CO2. And that CO2 increase is ultimately caused by us. We say it's anthropogenic. So anthropogenic in the sense that humans are driving this increase in greenhouse gases, and those greenhouse gases, like carbon dioxide, are increasing the temperature of the Earth's surface, and that this process of warming will continue unless there are sustained cuts in greenhouse gases. So I didn't make that up. I didn't actually make up the way of saying it. I paraphrased statements from the IPCC assessment. All right, and the 2 graphics you see, the two panels you see here at the bottom so I'll use this cursor in the hope that the people online can see my cursor. Are showing, these I pulled down in the last few weeks. So this is the estimate of the global mean temperature So when we say global mean, it's the global average of all the temperature from stations on land and ocean collected around the world and averaged each year. So each black dot here represents 1 year of data. And it's a very impressive data set because it goes all the way back to the end of the 19th century, 1880, and it continues up to 2017. And this shows the temperature every year. And there are features, if you've seen this graph, there are features that have become pretty familiar. An increase in temperature in the first part of the 20th century up to about 1935 or so, and then a decrease, and then sort of a plateau, and then a rise, pretty steady rise. In 2016, up here, it was the world record global temperature. For a few years, we didn't have much of a change in temperature. There was a bit of slowdown in the warming, and then 2014, 15, 16, it really shot up. 2017 is the second warmest year on record. And the idea of global warming as a theory, as a scientific theory, is that the driver of this temperature change, among other things, but the prominent driver of the increase in temperature is greenhouse gases. And this is a well-known time series as well. This is taken from a research station in Hawaii at Mauna Loa, atmospheric carbon dioxide concentrations from 1960 to 2020, and you see the steady rise of greenhouse gases, and we're driving this. It's human emissions that are causing this. So this link, so the theory of global warming says we see this, we detect it, there's no question, and that it's driven by this. And that assessment is based on models and observations, and that's what I'll talk about for the most part. Okay, so that's what we know scientifically. That's the scientific foundation. Of course, I'm not telling you all the whole story, but just kind of to paraphrase. What does it mean for us? Okay, so there's another part of this assessment that talks about the impacts of climate change, what climate change causes. Because all I showed you in the last slide was just temperature, right? So it's getting warmer, what does that mean? So if you look around the world, you see impacts of global warming on natural and human systems, okay, socioeconomic systems and ecosystems everywhere, right? So not all systems are affected, but many systems geographically dispersed throughout the world. And then there's some examples in this report. For example, the range and abundance of various species are being affected by climate change and global warming. If you look at agriculture, you can see that global warming, the warming that we're seeing and other impacts are affecting crop yields in a negative way, on balance, right? So the report sort of broad enough that they consider positives and negatives. And then there's also impacts on, for example, water resources, all right? Water resources are affected by a variety of factors, including precipitation and snow, okay? There's a statement about water resource quantity and quality being affected by global warming. And it's generally a degradation of amount or quality, and there's less confidence on this statement. So I just slipped this in to say that these statements are also accompanied by statements of how well we know. There's levels of uncertainty are often communicated with these statements. These are all paraphrases from this working group. Okay, so that's the kind of thing we know. Let's move on. Let's talk about what's unsettled. All right, so if we know all this information, why do we need to do more work in this area? So what's unsettled? Well, lots, okay. One of the key things that we're really interested in right now is how climate extremes might change. Okay, so climate extremes include things like high impact weather events, really strong windstorms, very strong amounts of precipitation that cause flooding. Droughts also count as climate extremes. Those kind of events are harder to quantify and harder to judge scientifically, and so we need lots of research in those areas to really understand how the extremes will change. The other aspect of climate science that's very uncertain is how climate change will play out on regional scales. I showed you one graph of global temperature. As we go down to different regions around the world, Canada, okay, the Arctic, even provincial levels going smaller and smaller, what climate change will mean for Toronto. As we go to smaller and smaller scales, we feel less certainty for natural reasons, because as you go, maybe those of you who've done some statistics or know about it, that if you have a smaller and smaller sample, you have more uncertainty that accompanies it. So that's one of the basic reasons that we have to do more work to really understand what happens at regional scales. One of the themes I'll pursue in this talk is related to useful information. How can we extract useful information for planning purposes and for prediction from our current tools? That's actually an open research question that we pursue in climate research. The next topic, and I can list many more, is surprises. What if there's an abrupt climate change? An event such as a very strong and sudden melt of the ice sheets on Greenland or in Antarctica that cause sea level rise? What if there's some other very large warming, something else that happens? How will we deal with it? How far can we predict it in advance, even though it's a surprise? And there could be technological advances that we have to deal with, or we have to be dealing with the impacts of different protocols for solving climate change. So for example, the Paris Agreement, that I'll mention later, talks about limiting global warming. How will we implement it? Well, that's actually an open research issue. And if we do implement it, how will it affect our daily lives here in Canada and around the world? The final thing I'd like to mention is that there are schemes, people have come up with schemes to control climate change through geoengineering. This is the idea of engineering the Earth's climate by putting in different forms of pollution. And that would be deliberate intervention on the global scale by nations or maybe groups of nations to change the Earth's climate. How that's done and how the system will respond and what that means, that becomes another kind of a set of questions to investigate. So, okay, so there's no lack of questions, right? There are many, many questions. And I would argue that any of these, actually any sort of these threads of questions really merits a lot of investigation. So we can recognize that there's an urgent need to cut greenhouse gas emissions. We know we have a lot of that information. Yet we still have to dig in more to really understand what the implications of all those decisions will be and what other surprises might lie in wait for us as we kind of go into the situation of more and more climate change. So that's the background I come at this with. And I argued, we had a chance to talk to the Canadian Association of University Teachers, and I showed some of these slides, and it was actually a nice opportunity for me to think about, well, why do we do this research? And then another flip side of this discussion was asking about how Canada has invested in climate research. So Canada has a long history of work in weather and climate. How, around the world, there's what's called an enterprise. It's a kind of business term they apply right now. There's the weather enterprise, which consists of all the observations that are made by satellites and by airplanes, by ships, that are all pulled together and used to help generate weather forecasts. And now, increasingly, there's more emphasis on climatic forecasts. So Canada contributes to that worldwide enterprise through the World Meteorological Organization and other international bodies. And so Canada contributes infrastructure, measurement systems. There's funding for government labs, for university labs, grants that people like me can take advantage of. And there are a lot of partnerships. This is something we hear a lot about in research. So this field is driven a lot by partnerships because we rely on public investment to make all those measurements and create all those tools. And one funding pot of funds that I was able to access, and I was very fortunate to receive this funding, was called the Climate Change and Atmospheric Research Program, CCAR. And it funded 7 networks for 5 years at about $1 million per year for each network. And I led one of these networks, the CanSice network, Canadian Sea Ice and Snow Evolution Network. Okay, and so I thought I would give you some background on CanSice, but I thought it would be better first to kind of give some scientific background. I haven't really given you any science yet, so it is science for peace, so I do have to give some science, right? So, okay, so what do? Well, you hit the books, you start studying it. Well, every lousy professor gives a pop quiz, right? So we're going to start with a pop quiz before we get into the science. Right, so are you ready? Prepared? You've got your pencils out? Well, okay, it won't be too hard, and I'll give you the answer right away, so don't get anxious. All right, so what I'm going to start with is a table I downloaded from the Department of Fisheries and Oceans in Halifax. Sorry, I didn't download it from Halifax. This is a table relevant to Halifax, and it shows the forecast of tides in October, but not of last year, of this year, October 2018. So this slide is a little bit old, I'll admit, but I could actually download this slide for February 7th, 2019 now. And what it tells you is the expected high and low tides in either meters or feet, okay, on different days. All right. So if you're a mariner interested in knowing the high and low tides, you can look this up a year in advance. So it's a great planning tool, right? This is a kind of a really striking thing, and it actually works. I mean, they wouldn't put this information out if it wasn't valid. So this is done all around the world. Tides are something that we routinely, and you've probably seen this kind of information, maybe you've even used it, but have you ever thought about what it means? It means that we can tell the future of the sea level, right, with two significant figures, right, 1.7 meters a year in advance, okay? So why can't we do that with weather? I mean, wouldn't that be great? Just look up the weather a year in advance. Right, so this is the quiz. All right. So why don't we have weather and climate forecast tables for many months ahead? And I'll give you three choices, and there's only one correct answer. First possibility is that, well, weather and climate scientists like me, we're just not that good at our jobs. You know, we're kind of dumb, and so we're not clever enough to forecast weather, a year ahead. Right, that's one possibility. The second would be that weather and climate are harder to forecast than tides. Just an intrinsically more difficult problem. And the third is that we lack good observations. So would you care to hazard a guess as to which one I want you to say?
B.
B, good. All right, amazing. You get it. If I had an apple, I'd give it to you. So yes, so the thing with weather and climate is that they're intrinsically harder to forecast than the tides. The tides are a very regular phenomenon that are governed by the gravitational pull of the sun and moon on the earth, moon primarily, and the sun on the earth. And we have ways of predicting it that are based on basic astronomical concepts, basic physics concepts. But weather and climate are different. And I'm not going to explain all the ways they're different, but just I think that key thing is, and I think we know this, that weather is intrinsically harder to forecast. What I wanted to do by way of answering this is to kind of show you in operation what, and at the risk of being a little complex here, what weather forecasts have done over the last 30 years. So this is from a very nice review paper that if you want to get some more background, I encourage you to look at. Gilbert Brunet is the director of the Meteorological Research Division of Canada in Dorval, Quebec. And I think that he was responsible for the Quiet Revolution part of this title, Weather Predictions Quiet Revolution. That's the actual title of the paper with that Quebec context. But what's shown here, I won't go into all the details here, but this is a measure of skill of the forecast. All right. So basically, when this measure is at 100%, the forecast is, for all intents and purposes, perfect for this particular metric that we're looking at. But what's interesting here is that if you look at the quality of the forecasts, all right, going from the 80s up to basically the present time, you can see that as time has gone on, our forecasts have gotten more and more skillful. There's lots of other information in this, but the main thing I want to point out is that the forecasts that are for 3 days are shown here, and for 5 days ahead, and 7 days and 10 days ahead. You can see that before the 1990s, we really didn't even bother with 10-day forecasts because it was just too unpredictable. But now, as our models and satellites have improved, we're actually getting to the range that we get basically about half the skill we can from the 10-day forecast. So that's actually, every extra day of lead time you get for forecasting is really useful, right? You get an extra day to prepare for bad weather or good weather. And what we also learned from this is that about every 10 days, every 10 years rather, we get 1 day of skill. So in other words, a forecast that we made for 3 days 20 years ago, now we can get a forecast all the way out to 5 days. But this is humbling. This is 1 day per decade. There are many, many people working on this problem, and there's a lot of investment. What I've shown you over here is kind of how these forecasts are generated, just schematically. We use observations, we use models, and we create forecasts. The models the observations involve 100 million observations every day that are brought into the weather forecast models. Went ahead on my graphics there. The models, the data that's brought in from this includes satellite data and airplane data and so on, weather balloons, all that, they're all brought into something called a data assimilation system, which actually brings the data into a format that the models can use and generates a forecast by making sure there's consistency between the observations we have and the models. So there's a lot of correction going on. And we produce forecasts that actually give you, if you know what a terabyte is, right? Maybe you have a 1 terabyte hard drive on your computer. So the forecasts actually provide a huge amount of data, 10 terabytes a day, but with that's produced every day, basically every forecast. And that's produced by many weather centers around the world. So there's a lot of data that's flying around here. But the scale of effort, each of these weather centers might have, maybe 100 to 200 employees, and there are several of these weather centers. And the rate of progress is slow and steady. It's not dramatic. So what it takes to create this kind of forecast, there's a recipe. This is another attempt at humor. Okay, so what's the recipe for a good forecast? You need high quality observations that are sourced from around the world, right? Just like in a good restaurant. You need fresh models. That's the best I could do. The models have to be kept up to date. You have to blend the ingredients with this special technique called data assimilation. So that's the chef at work. And then there's seasoning, and the seasoning is this chaos. All right, chaos, the unpredictability of the weather. Now I have a few slides, and I think I'll probably skip them about the chaotic part of this of this. But the main point I want to make is that we are the reason that weather and climate are hard to predict is because, in large part, not just because of the size of the problem and the many observations we need, but also because the atmosphere is intrinsically unpredictable. And it has this sensitivity to small changes that make it unpredictable. So weather is hard to predict, but climate is governed by the statistics of weather, and that makes the problem tractable in a kind of ironic way. So I'll skip one slide for, what's the name of the fellow in Montreal?
Stefan.
Stefan, I'll skip a slide and I'll go to this one, which is number 20, and give you a sense of how we do environmental prediction beyond just weather prediction and going into prediction of seasons, prediction of years, and prediction of decades. So the way it works in terms of a scientific enterprise is you have, there's my cursor, okay. You have to worry, if you were coming at this as kind of a designer or an engineer, you have to worry about what time scale you're interested in. Are you interested in tomorrow's weather? Then you develop one kind of system. If you're interested in the climate for the next 20 years, or if you're trying to understand climate a million years ago, that would be a different time scale. You have to decide which kind of variables you will include in your system. You have choices there because do you want to explicitly include all the atmospheric variables? Do you want to include atmosphere and ocean? Do you want to include snow or not? Do you want to include sea ice or not? You make these kind of choices. And then once you put these things together, you develop a theory. All right? The theory is maybe mathematical equations or physical equations, even statistical relationships that you build into the model to make the model kind of something that represents your theoretical understanding. The theory that we use is often the theory of fluid dynamics. So physical principles, we learn about how light propagates through the atmosphere, and we try to put that in the models. Many other things, cloud processes and ocean circulation and things like that. And the last part is the technical bit. That's the really time-consuming bit, and that's putting it all together, putting it on a computer, creating programming code, figuring out how to make it accurate and how to make it run fast so that we can get a forecast every day, or if we need to produce a forecast every few years, how to make it run well. So it's a large enterprise involving many steps and many different types of people. It's big science, big data, all these terms you might have heard. Large teams, all right. So I worked in this field in the States. I was in a lab that had about 100 people working on climate change, climate modeling. And that effort had gone on for about 30 years, and it still continues to this day. It's a long-term effort with lots of updates from the science. Now in Canada, we have a department which deals with environmental prediction, and that's Environment and Climate Change Canada, ECCC, which used to be just Environment Canada, okay? And ECCC actually has a whole range of environmental prediction tools that are used for generating forecasts. And there's a distinction, right? There's the tools and then there's the forecasts. Those are two different things. The tools they have are what most of my work focuses on. So if you're looking at forecasts of 1 to 10 days, all right, just the weather forecasts that you access routinely, they have a system called the Regional Deterministic Prediction System and the Global Deterministic Prediction System. So these are weather forecast tools that are used in combination with other systems from around the world. When you go beyond the weather timescale to the seasonal timescale, so how many days are in a season? Roughly. How many days are in a season?
120?
90, right, yeah, 120, something like that. So now, so you can see you're going really outside a typical weather forecast to like many multiples of the weather forecast time length. So a seasonal prediction system is really distinctive from a weather prediction system. And Canada has one called CANSIPS that we've done a lot of work on, Canadian Seasonal to Interannual Prediction System. And the interannual means that they try to do forecasts out a couple of years. And then when you go to even longer timescales, you do this years to decades. And this is a model called the Canadian Earth System Model. And this is the one that does the predictions of global warming, all right? What happens when we add greenhouse gases to the atmosphere. So you can see there's a whole range of specializations, but it's a continuum. And a lot of the modeling components are common to all these systems, but they're not all exactly the same. And I'm going to show you here just a little bit more about the science, and just to show you that you can organize on timescale, weather, seasonal to interannual, decadal, multi-decadal, and then you can decide which components to include: atmosphere, land, snow, aerosol, ocean, sea ice. And I just included this for those who want to know a little bit more. And what I did with this orange information here is just to indicate that for some applications, you really need to know the initial state of the atmosphere and ocean very well to do certain kinds of forecasts. And other kinds of forecasting going very far out, you don't need to know all those details. And that determines a bit about how you set up your system. So the more observations you need, actually, the more expensive the system is, because you have to get a bunch of observations to agree with your model at some initial time. But if you're just interested in general statistics, you don't actually have to worry so much about having exact agreement with the observations at one time. This is something that's a little, like, we can talk about it if you'd like. It's a little hard to explain in a short talk. Okay, so this is kind of my domain of interest. It's looking at the components of snow and sea ice and looking on these timescales from 90 days to longer. And that's the Canadian Sea Ice and Snow Evolutions Network's domain. We decided to look at snow and sea ice, and we're trying to improve prediction over these timescales from seasonal to interannual to decadal to multi-decadal. Okay, well, why? Why do we need a network on? Why do we need to focus our research on this? And there are lots of reasons you could think of, but basically, snow and sea ice are a defining characteristic of Canadian life. Okay, our history, our culture, our identity is really tied in with snow, less with sea ice, but sea ice is really important for the northern peoples. And sea ice is actually a big, if you look through the whole history, it really is a big part of our identity. Actually, if you look at global climate, a scientific reason to study snow and sea ice is that it's a critical part of understanding the way the world will respond to greenhouse gases, to the global warming problem, okay? Because sea ice and snow are very sensitive to climate change, and they're bright, and they make it harder, when sea ice and snow retreat, that makes it easier for the system to absorb more solar radiation, and that's a positive feedback. Another thing about snow and sea ice related to the point I just made is that there are rapid changes observed. And just to give you a sense of those observed changes, this is taken from my colleagues at Environment Canada. I'm showing you the difference between two 10-year periods. This is basically the last 10 years up to 2015 minus the 1980s. And I could do this kind of plot for different periods and get basically the same answer. So this is roughly 35 years of change. And what we've seen, so what I'm showing you here is the amount of snow expressed in percentage, so how much snow cover there is at a given point, and how much sea ice cover there is. And what we're seeing is that over that 30-year period, we're getting reductions on the order of 25 to 30% annually. And over the sea ice region and over the land, we're seeing reductions in snow cover of about 5 to 10%, which is a lot if you think about the overall snow cover and how much is lost, but especially the sea ice, it's been very dramatic. You even see regions here where there's been a little increase in sea ice. I mean, you see different features. Over here is the duration of the snow season and the duration of the sea ice season. So you think of the duration is something that's easy to understand once you've thought about it, but it's just how long, once snow sets in, how long does it stick around? That's the duration. And sea ice similarly, once the sea ice forms, how how long does it hang around. And this is showing basically all the brown colors are reductions, and each gradation is a reduction of 1 or 2 or more weeks. 1 week, 2 week, 4 week, 8 week, 16 weeks. So what we're seeing over this 30-year period is that the sea ice season is shortening by 10, 12 weeks in many, many places, and the snow season is shortening by a couple of weeks. So that's a real driver of this whole network, is we see these big changes. And I'm showing you some observations, and I'm not showing you the uncertainty here, but take my word for it. I'll show you examples. There's a lot of uncertainty about how snow and sea ice are changing because of observations and because of the models. So CANSICE, I mentioned already, 5-year partnership, 7 universities, U of T, and I can list them all, but I won't because I'll forget one and bother somebody. But universities across Quebec and Ontario and BC. We are partnered with Environment and Climate Change Canada, and it's been a very effective partnership. It's been great working with them. It's funded through NSERC, and the purpose is to advance our capacity to simulate and predict sea ice and snow. We really chose this focus, and we are looking at 2 models, this Earth system model for looking at climate change, and this seasonal to interannual prediction model, which focuses on the seasonal forecasts. So we weren't just out to explain climate change or make us our understanding of that better. We were also interested in developing products that people could use to improve their predictions for just a season ahead, which helps a lot of people. So we had that kind of two-part focus. And so we had basically $700,000 a year to play with. So we tried to have worthy goals, and we split our research into basic research and then sort of synthesis of research that would lead to applications. So our basic research was focused on prediction, on understanding here. This processes means that we're trying to understand the processes in the climate system. And this attribution bit here is to say that we're trying to understand which changes we've observed can be attributable to human influences or other factors. We're also interested in the Western Cordillera in BC and looking at changes in snowpack there and how that's impacted water resources. And our synthesis topics here, this is pretty abstract, I know, but basically what we were trying to do was we had a lot of research projects that were scattered around the network, and with our synthesis products, we tried to pull them together and create cohesive reports. So I'll show you a couple of examples of the kind of research we were doing. First of all, this is a typical kind of everyday map we would look at, all right? Let's just start with a very, very top row here, okay? On the left column is observations. On the right column is our model, the Canadian model CANISM, all right? What I'm showing you here is wintertime temperature averaged over a long period, 25 years, in the observations in the model. And you can see that the model, so what we're seeing here is temperatures that go down to -30 or so up here, and then around 0. So this is like the Arctic is cold, southern Canada is warm. It's colder in the middle of the continent in winter than on the edges, right? And that's just a natural part of our seasonal continentality. And you can see that actually the model captures that kind of general behavior with differences, right? And the differences here have to be seen in context, because if you look at precipitation, so in precipitation, we get lots of wintertime precipitation in British Columbia and here in the Maritimes. And you can see that the model, see there's 90 millimeters here, 70 millimeters. So we're expecting around 70 millimeters or so. And the model's giving us a large region where there's a large precipitation bias. So we see the model has a problem. The model is not perfect, right? That's something we know of all models that we use. And this is a measure of snow. I apologize for the acronym here. Snow water equivalent. It's the amount of snow that is expressed in terms of the amount of water there is. So if I look at my glass, right, a glass of water here, or this, if you translate this into snow, you get a snow layer maybe that big, maybe a bit bigger. All right. So that in snow depth, but the nice way to sort of relate different snow quantities is to pretend the snow is melted and express it in terms of millimeters depth. And you can see that the model has, it's wetter on that. It has more snow here in the BC than in the interior, which is good. But you can see that there's a bias. We do more than this, and here I really will skip. But what we try to do is put all the statistics we do in the context of other models. So for example, the green point here is the Canadian model, and all these other points here represent other models from around the world that are trying to do the same thing. And basically, the farther these points are from this black dot, the worse they are. So you can see that in temperature, Canadian model is pretty good, but it's not that good compared to other models, but it's reasonable enough. And this is the snow thing that I showed you before, and you can see that the models are really far from observations as a whole. And the Canadian model sort of sits in the middle. So the Canadian model is not great, but none of the models are really good. So you can see by comparing temperature to snow that generally the models have a harder time with snow. And these points here in the black with the black outline are actually 4 different estimates of the observations. And you can see that the observations are actually far, and this represents the kind of average of the observations. You can see the observations are far from each other. They don't agree. So when we are trying to assess the models, we have to look at how certain we are of the observations. In this case, we know that the snow observations are actually very hard to put together and come up with a consistent picture. Another kind of analysis we can do is look at how snow varies from October, November, December, January, February, all the way out to June. This is the total amount of snow mass over Canada, okay? And this is in the observations, and you can see we put the shading here indicates our range of uncertainty about the observations. You can see that it's pretty big, right? And here's the Canadian model, and we can see the model has too much snow overall. This green point represents the Canadian model. The red points represents other models. So I'm not providing this to give you, I won't ask you, there will be no quiz on this figure, all right? But it's just to show you the kind of work we do every day to assess our models and make sure that they're providing a quality simulation. Here's a not so subtle problem. This is sea ice. This is the trend in sea ice observed in terms of the total sea ice area extent between 1980 and 2015, roughly, in orange. And here are the average of all the models, all right? You can see the models tend to kind of get the basic behavior of sea ice. Unfortunately, here's the Canadian model. It tends to have a very low sea ice, amount of sea ice, all right? This is in the Canadian Arctic. And so we have to sometimes we have to face problems in the models. The Canadian model is about to be upgraded to a very different sea ice and ocean component. And so we think this will get better, but we had to say, well, this is where things stand right now. But I don't want to give you too negative an impression, because even though the models have flaws, we can still use them for useful purposes. So I think what I'll do next is I'm going to skip one slide go to slide here, to this slide. So I was going to show you a couple of ways we use the models, even though they're not perfect. This is a product that was developed as part of our research by Bill Merrifield at the Environment and Climate Change Canada. And we didn't know this at the beginning, but it turns out that Environment Canada, actually nowhere in the world did they have a forecast of what the next season's snow would be on a national scale. So seasonal prediction was mostly focused on temperature and precipitation, but not so much on the snow cover. So we actually have the first snow cover forecast in Canada, or sorry, in the world. The Canadian forecast is the first one in the world. And this is the kind of game you play. You generate a forecast. This was a particular forecast for January 2016. The blue indicates more snow than normal. The red indicates less snow than normal. And this is the verification. It's turning to the observations and asking, well, what actually happened? All right. So this is called a hindcast because it's a forecast made in the past for the purpose of developing this kind of product. And what this says, it's a proof of concept that we can actually predict, come up with useful predictions of snow. And the research we did helped assess the quality of the model and figure out where the biases were so that Bill and colleague could do a better forecast. And I did give, I sort of trashed the sea ice simulation, and I don't know if you picked that up, but I said some bad things about the sea ice simulation. But the fact is that Michael Sigmund, who worked with our network, was able to use the sea ice simulation, as bad as it was, to come up with forecasts of how much in advance we could forecast the retreat or advance of sea ice. And this is another product that's in development for Environment and Climate Change Canada. So that was a big part of our network, was looking at the climate change problem, but also looking at shorter time scales to really get some good information. I apologize to you up in the balcony because I've been looking down here, but there are folks up there, so I acknowledge your position. Okay, so I wanted to kind of switch gears to the final topic to bring your attention to, and that is looking at future projections of climate change and the Paris agreements. Okay, so just to give you a little bit of background, so the Paris agreements was a kind of a worldwide decision by under the framework of the United Nations Framework Convention on Climate Change to limit the amount of warming that will happen to 2 degrees Celsius, but preferably to 1.5 degrees Celsius. When I say warming, I mean global warming. So the target of the UNFCCC, the Paris agreements, is to say we have a number, that number is 2 degrees, we should not go above that number. Now, they didn't say anything about how to get there or anything like that. That's a different set of ideas. But the main thing they asked the scientific community to do was to go off and figure out what does 2 degrees of global warming mean for different areas of interest. Okay, what does 2 degrees of global warming mean for Canada? What does it mean for the Arctic or other regions? What does it mean for sea level rise? So the UNFCCC, FCCC, I guess, asked the IPCC, this is the research assessment body, to report on this. And so what our network was just at the end of its life, but we decided to pursue this topic a little bit. And we came up with a project called North to Warm, all right? And it's so it's kind of it's an attempt at humor, but it's kind of a multiple entendre here. So the idea was that we were trying to understand the implications of 1.5 degrees Celsius and greater warming for the Arctic. And this is the project N2W, okay? And what we were trying to tackle with this project is the idea that for people who have stake in the Arctic, and that includes Arctic peoples, but also governments and industry, understanding what these Paris targets mean is very important and very challenging. The key challenge is that we know that as the world will warm, I showed you a version of this graph before, that the Arctic is warming faster. This is the blue here indicates the change in temperature in the Arctic. Basically, the Arctic warms at double the rate of the global temperature. This is a phenomenon called Arctic amplification. And so we knew there were going to be lots of impacts on the Arctic. We'd analyzed them in our network's research to this point. And so we decided to really focus our attention on this issue. And it turned out to open up a large can of worms that we're still dealing with. But I wanted to show you some of the results of this research, just to give you a flavor for where we are now. It's hard to see these colors on the screen, but what we're showing you here is the temperature change projected. This is a model-based estimate of the temperature change that will occur with 1.5 degrees of global warming and 2 degrees of global warming over the Northern Hemisphere, but focused on the pole. So this is Canada, but it's actually showing you the whole Northern Hemisphere. And the colors, I'm sorry they're a little hard to read, but you can see 2, 3, 4, 5, up to 7. So what this tells you is that we will expect several degrees of warming if the world gets to 1.5 degrees. And the context here, as I mentioned before, and maybe went by fast, is that we've experienced 1 degree warming to date, about 1 since the pre-industrial era. So 1.5 is about 50% more than we've experienced to date. All right, 2 degrees is about double what we've experienced to date. So there's a couple of expectations here. One is that if you double the amount of warming, maybe the regional impacts will be doubled. That's kind of a hopeful statement, and sometimes that works out. But sometimes those regional impacts will be larger because the system isn't quite so linear. So that's the kind of thing we're trying to assess. So this is well known that when the world warms a certain amount, the Arctic will warm greater. So 1 degree here is the difference between these 2 shades of orange. 1.5 is there. So you can see that over most of the northern regions, and certainly over most of Canada, we expect 2 to 3 degrees warming for 1.5, maybe 2 to 4 is a better number. And then up here in the Arctic, if we go to 1.5 or 2 degrees, we're looking at 5 or 6 degrees Celsius. That is huge. That's enormous warming. So, and then the 2 degree is kind of supposed to be a guardrail. I've heard that word used. You're not really supposed to go past that. Unfortunately, the prospects are not clear for staying under even 2 degrees, but that is a different issue. This was another part of the assessment, was to look at the impact of 1.5 or 2 degrees on our snow season. I mentioned how our snow season has been observed to change. And this says that if we go to 1 degree warming in southern Ontario, we'll have a snow season that will be about 3 or 4 weeks shorter. Same with BC, right? And those kind of reductions also play out in the north. And those are exacerbated as you go to 2 degrees. So they get 50% more than 1.5. Other games that we played, I shouldn't call them games because it's a serious business, but we've looked at the impact of melting days that would lead to degradation of conditions for ice roads in Canada's north. We've looked at the Canadian Arctic archipelago and how many ice days free of ice we might see there, which is relevant to ecosystems and transportation. And then we started doing something really hard, which is to work with social scientists to say, okay, well, what does all this mean? And when I said the can of worms, the can of worms is that as you broaden out as you get less focused and more trying to understand the broader implications, you run into a situation where you're really at the limits of what's been done so far. And so we realized we didn't have the resources to really address these problems in full, going all the way into the impacts and what the socioeconomic impacts. But I showed this table just to show you the kind of things that people are thinking about out there. They're thinking about shipping, safety risks for travel over ice. They're thinking about implications of permafrost degradation for infrastructure, that snow cover could impact road and lake ice, that impacts the transportation that occurs in the north. It impacts construction and fisheries, and many other aspects of daily life in the north. So this is just to give you a flavor of the conversations we've been having. So our team was largely physical climate scientists with a couple of social scientists. They weren't just thrown in, they were really good people. But we really realized that we're really at the limits of what we can do with kind of the limited time we have left in our network. And that kind of brings me back to the sort of final point I want to make about the future of climate research. So I would, we've had this funding and it's been very good. And we talked about the political context a little bit before I started. Politics aside, if you kind of look at the long-term trend, climate research has been funded in Canada for decades. And the funding pots have oscillated between governments and universities and industry to some extent. But my observation is that funding pot has been getting smaller as the problems and progress we're making has been getting greater. So it's a very strange situation. So this is my point here, that the partnerships fund, especially even with partnerships, which seem to be always leveraging research, that money has declined. And right now, as a very biased witness, somebody who's been benefited directly from the program, our program was not renewed. We had the government of Canada sponsored an evaluation, and it was well evaluated. We trained hundreds of students and postdoctoral fellows. Our network, 90% of its funding was dedicated to training people. We didn't do very much field work, but we did have a really large cadre of people who are now leaving Canada and finding positions elsewhere as they can. And we've tried to make this work. So one of the things that I wanted to mention here is that we're trying to sort of develop more of a longer term perspective on this situation. It's not simply one political party or the other. It's really that there is a lack of awareness of the kind of research that's needed to really deal with climate change. And so there's a group that I've been leading for the last couple of years, actually since 2015, time flies, atmosphere-related research in Canadian universities, ARCU. It's kind of a funny title, but there's good reasons for it. And what we decided to focus as kind of a common theme is that we're interested in weather and climate and air quality dealing with pollution and the air quality of the air you breathe. That research to benefit Canadians in a time of rapid change. All right. So the changes I've talked about in snow and sea ice are just one example of the many environmental challenges we're facing, right? We have tools to do quantitative prediction. That to improve those tools, I think is really urgent, and it needs support to do that. So we have some documentation, which I include in the last slide in this slide deck, which I guess flash up at the end. So just to kind of recap. So we have, I think, enough information to try to tackle global warming as an environmental problem, but we need to invest more in really understanding the problem and making useful predictions for people to act on. And we've had 5 years, and I think we've made a lot of progress. So I know I'm tooting my own horn here, but I think it's really important to say that the 7 networks and whenever Canadians are given the opportunity to do this kind of research, they really do a good job, and they play at the international level very well. And we have all this, we have a funding issue where we're about to go to a funding gap, and there is need for a short-term maintenance. But we're in agreement with the federal government is that we need a longer-term plan. And so we're trying to deal with that. So that's all I have to say. The last slide, for those who are online, is just a list of links and so on about CCAR and so on. So that's all I have to say for now, and I hope I haven't taken too much time. But
No.
no.
Thank you.
Thank you. Thank you for your attention.
Now we're going to have questions.
Okay.
You're going to call on people.
Oh, I will. I see. I'm chairing. So. Yes. Yeah.
I have one for now, but you mentioned the snow water equivalent. Is there a unit that talks about like an ice water equivalent?
Yeah. There's ice thickness.
Okay.
So the mass of ice, is typically measured in meters. I don't know. It's a good point. I don't think I have a. Did I show you an ice? No, I didn't show you an ice thickness map. So ice thickness is something that is really critical to understand because the thickness of the ice. I think I only showed you one. Yeah, this was duration, and this is aerial. This is just fraction. So the ice thickness. So you could have a very wide ice pack, but if it's all thin ice, then it's not as useful for people. Yes.
What slide number?
Oh, slide was 25, but it wasn't actually that useful for this discussion. I have other slides, but it would take me a little longer to dig them out. But so actually ice thickness. It turns out that ice thickness and snow thickness are harder to measure than ice area and snow area because you can see visibly with your naked eye, you can see sea ice and you can see snow. And basically the instruments in space that do that are just looking like they're just taking pictures. But the thickness, of course, is under that surface, and you have to use other techniques to figure that out.
Yeah, so what I'm actually asking about too, I'm interested in permafrost thaw.
Yes, yeah.
And
okay.
so that must be even more difficult to probably predict.
Yeah, well, permafrost is a really, anything to do with the land surface and below, so soil, it's super hard to infer properties of soil from space, but there are instruments that do that, but it's more soil moisture and aspects of temperature. But there are instruments that radar instruments and also instruments that operate in the microwave band where they try to get information about soil moisture. So all those instruments in space are measuring radiation coming up that's emitted from different surfaces, and they emit different powers and different frequencies, and they take advantage of that to measure those properties. But they all have to be validated on the ground. Yeah. Good question. Yes.
Yeah, tell us about the methane clathorates.
Yes.
And what, how scared should we be?
Methane clathrates. So the methane clathrate issue, I'm not an expert, right? So I'll start by saying
I think you're close enough.
I'm close enough, good enough. So what I know about that. So the methane clathrates are a form of, so methane is a greenhouse gas, which has been observed to be, actually there's very good work going on by my colleagues in my department, so I should know this. Methane has increased over time quite a bit, but not in the same way that carbon dioxide has, because methane is really biologically active and it's volatile. It has a shorter lifetime, and CO2 is very inert and lasts hundreds and thousands of years, but methane has a lifetime of about 10 years. And so what that means, that shorter lifetime means, is that If I emit some methane, I have a cow or whatever, for whatever source, it'll last about 9 years if nothing else happens. So the connection, and there's things that happen to methane that are related to human activity, but there's a lot of biological activity as well. So the methane clathrates are a particular form of methane under the ocean that are locked in ice, kind of an icy form. And the concern that you probably heard about was that as the ocean warms under climate change, and we have seen ocean warming, that frozen phase would melt and would release large amounts of methane. And in fact, the reason it was that theory was developed was that there were observations of past climates many millions of years ago where there were changes in temperature that might be explained by this methane effect, methane being released from the ocean into the atmosphere and being an effective greenhouse gas. Well, my understanding of that is that the research, of course, that it was a very, it was an explosive hypothesis, and there was a ton of research, and that the excitement has diminished a bit because it doesn't look like it's an immediate a problem. It's a source of, it could be a source of methane, but people, I think the last time I talked to an actual expert, I believe she told me that it was not going to be, that it wasn't at the critical point for that particular process. And in fact, other research that has been spoken of here at U of T suggests that that whole feedback was exaggerated. Not by the person, but the original analyses, exaggerated some of the impact. The other concern about methane is in thawing, of permafrost regions, and so there's in that case, methane is a product of anaerobic respiration from bacteria. I'm really getting outside my comfort zone here, but there again, there's a lot of uncertainty about how bad that source would actually be. My view on this is that carbon dioxide is actually a serious enough problem that we don't, there are going to be feedbacks that might make it a lot worse, but I suspect that our main driver will continue to be anthropogenic carbon dioxide. And one of the things we've learned over since this last assessment from 2013, where people realized that if we stopped emitting greenhouse gases, we actually probably would stabilize wherever we stopped. So we'd stabilize temperature. Of course, we're not stopping all emissions, but what people used to think, and maybe in the 80s and early 90s, was that even if we stopped emitting greenhouse gases, there'd be an inertia effect. Al Gore said that in his movie, actually. He said, they just keep going, right, like a flywheel. And that flywheel analogy just doesn't work. It's because there's too many feedbacks from the rest of the system, from the biosphere, that kind of control any sort of thermal inertia effect. So in other words, if we stopped emitting, we would actually not have more temperature increase. But unfortunately, the only way to reduce the temperature would be to remove greenhouse gases, and that's a very big challenge.
We'll talk about that big challenge, because that is really a very interesting notion of, reducing and locking it up someplace. How much hope is there for that kind of negative, emissions? I mean,
I've seen studies that it typically takes energy to, so you want to come up with a system that in the net reduces greenhouse gases, and it's just an enormous. The scale of it is it's beyond comprehension in a way. I've seen people estimate how much carbon tax you'd have to add to come up with a system that would reduce carbon dioxide. I mean, it's a set of chemical reactions that chemical engineers could figure out. And I haven't read the literature. I've seen one or two talks on that, and it was very back of the envelope. So I don't think I'd care to really speculate, but it's really tough. The other part just to say one more thing quickly, there's the other aspect of this, which is carbon capture from emissions, and that prevents you from emitting extra carbon dioxide. That's less speculative. It doesn't seem to work that well, but it is a way of controlling the amount we emit, but actually drawing it down. Sorry, there was a question here.
Question coming in from the internet.
Yeah.
It's from a Peter Shepard, and he talks about the sea ice predictions of decline, and he wants to know where ring seals are going to be surviving when the world is at 1.5 global mean temperature above normal.
Okay, I don't know where the ring seals are located now, but what I can say that there's a region. I don't know if that was my biggest map. North of, so.
What slide number is it?
This is slide 33. Sorry, yes, you can't see me with my cursor. The region north of the Canadian Arctic Archipelago and Greenland is the region where people have, there's an article actually in National Geographic you can look up. There's a region, it's called the last ice region. And if you look at ice decline as projected, the last region where there is going to be perennial ice or ice that lasts more than a season is projected to be in and I'm drawing sort of a triangle here for the people in the hall, but it sort of starts north of Greenland and kind of extends into the Arctic Ocean, and the boundary, the western boundary is sort of just to the west of the Canadian Arctic Archipelago. So I don't have an actual sketch for people, but it's sort of this region. What the reason the ice here is very thick, and its thickness is maintained by basically the pattern of atmospheric winds and ocean circulation, and that which pushes the ice up against these islands here and Greenland. And so the idea is that this is called the last ice region because it's the region where all the ecosystems will likely retreat to. And the future is not very far in the future. We're talking about 30 year kind of 30 to 50 year sort of envelope, to my understanding. The ring seals, I'm sorry, I don't know where they are, but if they live inside the Canadian Arctic Archipelago, a lot of that ice will probably remain robust for quite a while. It might get a bit thinner, slushier, but I don't think it's. But there again, it's just speculation on my part because it really requires us to understand what the models are doing. But what I would say is that in the Western Arctic and sort of Beaufort here, Chukchi Seas, that's where we're going to see. We've already seen a ton of decline, and the Arctic has just gone into open ocean, and that's where those kind of species are going to have a hard time if they rely on a multi-year ice. I wish I could tell you more, but it's a very good question.
Could you back up, because I didn't get all of that. You were talking about ring seals?
No, ring seals.
Ring seals.
The question was about a particular
polar bears
species,
and ring seals.
polar bears and ring seals, and I wish I could say more, but this is where the truth comes out. I'm a modeler. I'm a person who studied theoretical physics and was fortunate enough to get into this, with my own background to contribute. But actually, we're having a meeting there. If those of you are interested, there is a lecture, a panel discussion that is happening on. Is it today or is it tomorrow or the next day? Anyway, in the next couple of days. There'll be a panel on the future of the Arctic, and it's focused on sea ice and observations, which I can point people to if they'd like just after the talk. I should know, but I've sort of forgotten it by standing up here and talking too much. Yeah. Very happy to entertain. Yes, sorry, sir.
I try to divide my question.
Okay, yeah.
Maybe some of the question is just loud thinking.
Yeah.
I'd like to hear your thoughts about it. So our technology of prediction and observation has developed, let's say, in the last 100 to 150 years.
Mm-hmm.
So before that, how reliable are our observations? The reason why I'm asking this, as you mentioned, the weather or the climate is very sensitive to very small, tiny changes. And we know in astronomy that the size of the sun is increasing, the universe is expanding. So there are a lot of changes that may be not really related to our emission.
Yes. Well, I did say that the weather is very sensitive to tiny changes, but I didn't say that the climate was sensitive to tiny changes. So the weather, so weather systems, the forecasts we make, and it's not just the forecast, but the actual system. Small differences will, within 2 weeks, change the forecast, right? And we have examples. A good example is Hurricane Sandy, right? So a lot of the weather models, Superstorm Sandy happened in 2012, and that led to this weather system that went from a hurricane to kind of a mid-latitude system, and it slammed into New York City. The winds carried this storm surge into New York City. But the forecast for that was made about a week in advance, and some of the models showed that forecast and some didn't. And the key thing was whether the storm would turn left or turn right. And it was very sensitive to the exact conditions of the atmosphere that were steering that storm. So that's one kind of problem, right? But the problem of sensitivity, like a structural sensitivity of climate to small changes, it's not impossible, but that's not the global warming that we're talking about. Because global warming is sensitivity to a big change, all right? So put big in context. The impact of carbon dioxide is on the order of just a few watts per meter squared, 3 or 4 watts per meter squared, okay? This is like 3 units of energy. The total units of energy coming in to the Earth system are about 300, give or take, okay? So it's a 1% change. So that sounds small, but that 1% change leads to a temperature change of about 1 to 2%, but it's absolute temperature, which matters for us. So you could say those are small numbers, all right? But it's not this. But the thing is that if you look at the variations we've seen over time, this is a big perturbation. It's not a small perturbation. So I totally take your point that there are variations that I haven't talked about, which go, and that's why I started, with the basis of climate change being the expertise of the assessment, right? I can't sort of defend the whole field all at once, but if I go back to my fourth slide, I would say that this, the scientific basis of this extends back, and maybe you've heard this from other people, but it extends back to the 18th century, 19th century, where the first calculations of the interactions of light and electromagnetic radiation with carbon dioxide and other greenhouse gases led to these predictions. And in fact, it's inconceivable that we would have our current climate without carbon dioxide, which you probably also heard. And in astrophysics, these greenhouse effects are a key part of understanding how the current planets have their own temperature is really maintained by these kind of greenhouse effects, right? So then what we're really arguing about is whether these calculations that we're making are accurate. And I would argue that although the models are flawed, and I showed you some flaws, the global picture is not fundamentally flawed.
I'm not arguing that.
Yeah.
What my asking question is maybe how much do we know for sure how much is our contribution to that, or is it other factors that whether we are emitting or not is going to do the climate change? Because there are dynamics happening underneath the Earth, and there are dynamics that are happening in the universe.
Yeah.
And the moon is going further from the Earth, and all those are going to have some effect.
All those have effects, but what we're also talking about, it's a human problem, right? So what I think people are really interested in is what is the impact of our current emissions on the next generation or the next, say, 5 generations, right? Do we really care? If we look at past climates, we're really studying them because we want to understand the current climate. And there are lots of things we don't understand about past climates. I definitely agree with that. And so that's why we keep reassessing these observations. So my short answer is the scientific work that's gone into climate change so far suggests that these things are linked quantitatively the way we see with uncertainty. But your question is the uncertainty a quantitative measure, or is it a categorical? Are we missing something big, right? Like a methane cloud, or I've heard Earth has passed through space dust, and that's what actually governs the planet. I've heard lots of solar variations. This is way more robust, right? And that's why we have these big assessments. That's why so many people spend all this time. And if I guess the other, and these are all arguments other people have made, so but I would say that if there was an effect that somebody didn't, that if there was something really new, I know my colleagues, they would pursue it, right? The idea that, because there is an idea out there that climate scientists are closed, are kind of a closed group. And sometimes I think that any field has its professional sort of habits, right? So maybe that climate scientists are too closed to new information. But if you actually go to the meetings and hear and talk to people, and not just in the halls, but if you actually go to the talks, there are lots of controversies that are aired and talked about, and it's not that different from other scientific domains. So I don't think there's a huge missing piece of this 20th century puzzle. The controversy is really, for example, this feature here, why was there a temperature rise? Why did it stop? That's still controversial. There are lots of controversies, but they tend to go and leave the same answer. Yeah.
A question from Nathaniel Schooler in the UK. There was an article published in the Globe and Mail, and it was titled, "Without Funding, Canadian Climate Science is in Peril."
Yes.
Can you elaborate why? What are the pending threats that are yours?
Yeah, thanks for the question. All the way from the UK. It's late there. So yeah, that article was written by Ivan Semenyak, and he has been really good at highlighting this issue. So it was in response to an international campaign to draw attention to this issue of the closure of the Climate Change and Atmospheric Research program. And just to give you a sense, that program was, it was a one-off program. It was never promised to be a renewing program. And so that's fine. And so the crisis is that program filled in a gap that was left over from previous cuts that had been made under different combinations of governments. I mean, it's not all just on, it's not just one government or the other, but definitely we had a funding gap in between 2006 and 2011 or so, 2011 and 12. And this money, this $35 million, replaced a much larger source of funds, which was still not that much. I mean, you can all say you need more, but if you're comparing internationally, that the original Canadian Foundation was a good investment, a very solid investment, but it wasn't astronomical in terms of what people are doing around the world. We went to the Climate Change and Atmospheric Research Program, and that represented a relatively small amount of money, but it was something that kept the research going in Canada. And at this point now, there's been a cut, and the program wasn't renewed. It was submitted for renewal internally to the government, and it was not renewed. And what we're saying is a crisis, and I don't think it's an exaggeration, is that we go to the end of the funding cycle, and there's no follow-on projects. CanScience is done, basically. We're finishing it off. I'm very comfortable with that. I think we've achieved what we need to achieve, and we should propose new things. The point is that none of my colleagues will get the opportunity to apply for something, at least as of this year, and hopefully maybe next year, in the next budget, there might be some change. But that's the crisis. A crisis being that there's a real change coming, and we've laid off our people, and our people don't have other places to go to. So I wanted to just add, though, not to mislead you. What was the name? Nathaniel. Not to mislead you, I mean, there are regional investments in Canada. So the University of Saskatchewan has made a big investment in, and the Canadian federal government has funded the University of Saskatchewan very, very well in the area of hydrological research. And there are other kind of investments like that at some of the other universities, but there's no national program. And we argue that the national aspect is really critical to ensure that we can carry out this coordinated research that benefits everybody across the country, because fragmentation can be really dangerous in this field. We're competing with European groups that coordinate across Europe as a whole and do research that really brings them to the cutting edge. If we devolve to just kind of individual university funding kind of arrangements, that really detracts from our abilities to compete. And when I say compete, I really mean it. Science is extremely competitive, and we can't take for granted that we'll always have access to the best research results coming from other countries around the world. Their priorities will rest with predicting climate change in their areas. So I think Canada stands well to invest in its own research to make sure that we're covered and that we're getting the information we need.
I have a question as a green building expert.
Yes.
I often tell my clients that they need to be designing their buildings for the future climate.
Yes.
And we often use 30-year weather files to predict energy efficiency performance in our buildings. What's wrong with that idea, and what could we be doing instead?
We should talk.
Yeah.
Because I'm working with colleagues in engineering and in architecture. We actually put in a proposal to the government of Ontario focused on education of practitioners on exactly that issue. And that we think that I don't know the full answer, but we were just exploring that issue a little bit. And the issue is that, as you said, you have these weather files, you have these climate files. These are kind of standard inputs based on old norms. And all people do right now is just sort of add 2 degrees. They add a certain amount of climate change, but it's very speculative, and we don't know how, because we don't know how regional climate change is going to impact different urban regions. There's definitely something to be done there. And furthermore, it's the idea that will Canada still be a wintry country? I mean, it might conceivably not be. I mean, I know it's hard to take in all the information, and I find it very difficult too.
I saw the Toronto climate forecast, and they were talking about Toronto at a certain period of time being like Kentucky.
Yeah, exactly.
And that's basically where the snow stops on your way to Florida.
Right.
That's
exactly.
where you start losing the winter jacket, where you start going, oh, it feels like spring.
Right.
You can tell that the forests are more deciduous. There's less evergreens through that forest region.
Right. Yeah.
You don't see any maples producing maple sap. Like, that's a very different climate than what we live in, what we've known as Canadians.
Exactly. So are we designing? Yeah. So the real answer to your question is, if we're looking at, so the 2 degrees, I think, we 1.5, it's maybe, it's not a precise time, but we're looking at ranges of decades, 2 to 3, 4 to 5, or something like that. We are, our ability to respond to that is really, I think it seems limited. That's one side of it. The other side of it, though, is I think once those changes set in, people might make decisions too fast, right? And they say, oh, it's warm now, right? Well, again, climate can always bounce back for long periods of time, for surprisingly long periods. So we want to get away from making decisions based on short-term fluctuations. Mm-hmm. We don't want to panic. I don't believe that that's a good thing. But we definitely thought that there should be some effort to, in fact, I think the building codes are, what I've heard is that Natural Resources Canada, or NRC, mm-hmm. The National Research Council, is looking at updating the building code and making it a kind of a living document. That's one of their, so that because of these, as part of the adaptation to climate change.
Yeah, I'd like to see future weather files.
Yeah, that reminds me of an extremely important point mm-hmm. about the government funding, which I didn't make, but I've said this in articles, and it goes back to Nathaniel's point. The government of Canada and this is before the current government as well, has committed a large amount of money for mitigation of climate change. And we are not advocating against that. So that's making it possible to come in with engineering solutions to help Canada adapt to climate change, or green infrastructure to reduce carbon footprint. We're not against that, but it's orders of magnitude different. So it's $22 billion has been promised over. I think it's over the next five years roughly for that, and that's great. But we're talking about 35 million versus 22 billion. that is the levels of investment we're talking about. 35 is actually a bit low. I really think we were thinking it should be like in the 50 to 70, something that would be, because we don't want to put too much money into research. It would expand things too fast. But we're saying that that's the kind of money that would actually help us keep up with the research on top of all the other steps that are going into really helping people deal with climate change, which is, of course, the bigger priority. Okay, no question. You want to help people deal on the ground with it. But if you don't have the good information from the research community, I think you're kind of acting a bit blindly. So that question is, it is something we talked about, but we didn't get funded. but we probably didn't have the best approach either. So yeah.
I have another one. This one's more local from Mississauga, Ontario. And Julia Morton-Marr says, I saw dirt from the atmosphere on the glaciers in Alaska. How much will this increase the ice melt? I guess it's a reinforcing loop that she's talking about. Yeah,
the positive feedback from deposition of like is again outside my expertise, but the concern is that deposition from the atmosphere. Deposition is the process of dust and aerosols settling on a surface, and deposition of carbonaceous black carbon, basically soot, settling on glaciers darkens the glaciers, and that's one of the feedbacks that are involved in climate. So when you darken a surface, it absorbs more sunlight. That sunlight absorption warms the surface more, and you get more of a positive feedback of that builds on the original kind of warming from greenhouse gases. So for glaciers, it's one of the sources that people really are concerned about. And I don't know the numbers for that, but it might be a sign. It also might be a sign that something's going on with the melting itself, because as ice ages and melts, it kind of gets darker as well. So, and some of those, they get concentrated. So it gets into the details of how glaciers kind of grow and decay. And that's way outside my expertise, but it's good observation.
Thank you.
Yeah.
How often do you encounter climate change deniers? Do you try to educate them with no lost cause? If you had Comrade Trump in here for now, what would you want to tell him?
Well, I think how often I encounter them, I don't think my answer will mean very much, because I would say that as academics, we tend not to seek out heterodoxy. Right? We just kind of stay in our bubbles a bit. So I'm saying me, I don't know your background. I wasn't I wasn't trying to imply that you were in that position. I'm just saying myself and so we tend to go to conferences where people agree with each other, right? But when I've given public talks, and actually this is the most, I haven't given many public talks in the last few years, and this is the most recent one, very friendly audience. And I'm not saying you all agree with everything I'm saying, but you're very, very, very courteous and nice. So I haven't ever been in a situation where somebody's shouting at me and saying, you're talking nonsense, it doesn't matter. But I do like to emphasize how useful this stuff is for making shorter term predictions, and that it's the same tools. I really like that continuum from weather to seasonal to multi-year, because you can say, oh, I don't like weather modeling, I don't like these climate models, and you can say, well, yeah, but you evacuated your home when you heard the warning about Hurricane Irma or whatever. You responded to weather warnings before. It's the same kind of science. So that's the kind of tack I take, is that there's actionable information. And the climate, when climate forecasts were first generated, there wasn't very much information that you could act on. And so that's what we're trying to move into now with the engineers that I'm talking to now. We do have some funding to look at the impact of changes to extreme winds on built infrastructure. And there might very well be climate skeptics, and my colleague isn't a climate skeptic, but there might be climate change deniers who are in those faculties, but they might recognize that there's a need to understand this problem. So I think it's complex. When it comes to really vested interests, or dealing with people who are just absolutely recalcitrant, I mean, can you really change people's minds with information? I don't think so. There has to be something else, and I don't know the formula for that, but it's a bit more it gets into the side of emotions and motivations, and that's very tough. Well, there's one thing, yeah, there's one back there, but yeah, okay.
Sorry, I was stealing another one, but
No, that's good.
if there was more funding, would it be possible for northern communities to hire more people to involve themselves in this sort of like climate reading, and are there specific technologies that could be easy to use and implemented to better these models?
I think so. I think that there's been a recognition that this kind of research we're doing, I mean, the models spit out information about the Arctic, right? They're global models, so this is what they do by themselves. But I think there's it's a challenge to balance the effort to help people on the ground, right? And then determine what there's the helping side, and then there's the actual useful science side. And I think what's happened recently is that there's big investments in like education research in the north, and that it's permitting a lot of the observational work to happen, just be more locally controlled. But believe it or not, though, it's not just this, like this particular climate area. I mean, I've spoken to people who do work in seismology, and they'll just go and work with the locals wherever they happen to be. It doesn't matter if they're in the Arctic or wherever. So I guess what I'm trying to say is that it's when people are trying to validate sort of models and satellites at this scale, it's really big picture, and you have to coordinate across boundaries, right? And so far, there's not been that much effort to make sure that every community that's kind of that's affected by the research is actually involved in the measurements. Where it seems to be maybe more successful is when you identify issues that are relevant, climate-related issues that are relevant, and that you need good measurements for, and you get people involved. Unfortunately, I don't know the programs, but sometimes it's been awkward. Like people, the NSERC will fund, any agency will fund something, and they'll say, well, there should be a community component, and it's artificial, right? Then the scientists are like, okay, well, what do we do in the community? And then you get these communities who are bombarded by scientists, and of whom they're pretty suspicious, right? Because obviously their motivation was not there at the beginning to help the community. It's just that they have to check that box. It's more nuanced than that, because they come in, and of course they're people of goodwill, and both sides have their merit. But it's a complicated set of politics. But I think the most healthy thing is for different regions, to like, and it's not just in the north, but in different regions, get involved in the measurements and so on. It's just the more people involved, the harder it is to coordinate. I don't think I'm giving you a very good answer, but it's not provoking, so I appreciate the question. Yeah.
What is your role at the ARRCU, the Atmospheric Related Research in Canadian Universities?
Okay, so that's an ad hoc working group that I chair. And we started it in 2014 as a pretty informal group to what we were inspired by is actually, it's a group in the US called the National Center for Atmospheric Research, and a governing body they have called the University Corporation for Atmospheric Research. And we saw that what they were doing is very effective. It's very heavily funded, so it's a different situation. But we liked the way the university community in the US was kind of trying to get a common ground across many, many different fields of research. And and also work between universities and government. So ARCU was started with help from several universities and with NSERC. And we had good support from Environment Canada as well. And basically what we've been doing now is writing white papers and writing papers, drafting ideas about what we would work on together. So my role, I've been chairing that for a while, and we have different focus groups that I don't chair, fortunately. One on partnerships with government, one on education, and how we plan to do education in atmosphere and atmospheric science and ocean science, and another one on partnerships with industry. So I do happen to chair the government partnerships one because of my experience. But what we're trying to do is get and train more colleagues into this. So actually, one of our achievements, I think, in that was that we wrote this white paper and we got 70 professors to sign on to it, which is a hard thing to do. It's hard to get 70 colleagues to agree on a single sort of science document. It was general, but it was a good start. So I think we have good support across the country for that. And right now, I don't know if I mentioned online, but I'm the executive of the Professional Society, the Canadian Meteorological and Oceanographic Society. I'm representing ARCU on that as well, but that's just because I'm wearing both hats. So thanks for the question. I hope that was interesting. The last slide of my presentation, which is slide 46, there's arrcu.ca has the white paper and a couple of other things we've written. And I'm happy to talk to just send me an email. My email address is at the bottom of this slide here, paul.kushner@utoronto.ca, and I'm happy to speak to the person who asked that question. Yes, Linda.
Let me push you in a place that beyond where you've gone.
Yeah.
The Project Drawdown has a list of the most to the least effective of about 100 types of intervention to reduce global warming.
Yes.
And the number one has to do with refrigeration. And the claim is that the coolants in the kinds of air conditioning and refrigerators that are commonly used now, those coolants can account for fully 1 degree of global warming, and that the challenge is not only to quickly stop using those coolants and replace them with something better, which they do have some more less dangerous ones, but not very effective ones.
Right.
But also to try to capture some of the coolants in the existing refrigerators that are going to be dumped and the stuff will get into the atmosphere. And, 1 degree is a hell of a lot. They say that's the top threat in terms of global warming. Can you comment?
I'm surprised that so the thing about those coolants is that they're very, like each molecule of coolant, right, is a very effective greenhouse molecule. It traps a lot of radiation per molecule. But in the net, I'd be surprised if so there's a couple things. First of all, you have to worry about how effective it is, how long it lasts in the atmosphere, or the atmosphere and ocean, but it's really in the atmosphere. So it's lifetime in the atmosphere, it's the term we use, and then how much is out there. So there's some super greenhouse gases out there, but they're really around in trace amounts. And so they're not as critical in the problem. So the reason that if you look at, there's a graphic that people show a lot, which is the most important radiative forcing agents. The radiative forcing is that thing that, it's a concept that says how much energy does each one trap and warm up the planet. And the most important radiative forcer remains carbon dioxide. There's no question. But carbon dioxide is extremely difficult to control. And so it could be that if you go to these coolant, and I don't know the Project Drawdown, so unfortunately I can't speak specifically to it, but if you go to other sources, you can reduce either current or potential impacts. And my understanding is there's this agreement that, I don't know if you've heard of this Kigali agreement. Okay.
Yeah, that's where they did it.
Right, exactly.
They got an agreement, but it doesn't reduce it from the existing things. They're going to stop putting it in there.
Exactly.
Yeah.
Yes. Yeah, that's right. And there's another piece to this which I think is really interesting, and it's related. It does follow on your point. It's that the old coolants we used to use were the chlorofluorocarbons, so CFCs, which have really long lifetimes. And the Montreal Protocol from 1987 and the follow-on amendments reduced CFCs. But why? Why did they reduce CFCs? What were they trying to fix?
Ozone.
Stratospheric ozone depletion that leads to ultraviolet radiation reaching the surface, right? So they're trying to fix ozone. They were trying to fix this other problem. It turns out that if they hadn't fixed it, we would have a disaster as far as climate change goes, because the radiative impact of those gases that we remove or that we controlled, if we let them keep going, would have actually overcome or been larger than carbon dioxide. And we didn't know that at the time. Or they probably knew it, but they hadn't done the full calculation. And they knew it was a really good greenhouse gas, but they didn't effective greenhouse gas, but they didn't know that how serious it was. So there's this whole set of calculations called the world avoided. In other words, if Montreal hadn't been put into place, what would we have encountered? And it would have been awful. Now it would have happened really fast, and maybe we would be a little further along. So CO2 is really insidious because it's kind of slow and steady. And there's other sources that people look at. There's a whole area of short-term forcings of climate related to the soot that the person online asked about, related to sulfate aerosol emissions, which are the things that make haze in the atmosphere and sort of brighten the atmosphere. When you get rid of those and do clean air, then you actually allow more sunlight in, and that warms the planet. So people are concerned about the impact of short-term forcings, particularly in the Arctic. And I mean, Canada is heavily involved in a monitoring measurement program in that called AMAP as part of its Arctic Council activities. So all those things are in play. I think with the interesting thing about thinking about those technologies is that there might be sources we haven't thought about, and it's worth So I just don't know the specific answer for there. Yeah.
Is there a link between Arctic sea ice research and predictions and Department of Defense? Because that's a large unprotected border in the north. Yes.
Yeah. The question, I realize that people online can't hear any of the questions. So
well, they probably can.
Oh, they probably can. Okay. About whether Arctic sea ice is a defense issue. Yeah, indeed. Yes, it is. I mean, so there's an ice service. Canada has a Canadian Ice Service in Ottawa that does predictions of sea ice conditions for shipping. And I don't know their exact interaction with defense, but I mean, sea ice is a big issue for defense, and understanding the future is as well. Most of the research I hear about is all related to shipping. Mm-hmm. The calls for research do also come from DND as well. So, but it's not just a Canadian issue. It's a global issue. And so, one of the geopolitical issues occurring as sea ice retreats, of course, is the opening of the Arctic and all the countries that are interested in running ships and whatnot through there and taking advantage of ice-free conditions. So it is unclear to me whether the research money that's been that they're cutting is going to affect that aspect, because I don't know what's going on the defense side to actually. I would say there's a successful project in Dalhousie, run out of Dalhousie University, called MybeBeeTV, and don't ask me to expand the acronym, but it focuses on marine extremes. And Environment Canada and MybeBeeTV and Fisheries and Defense have all started developing a common model for doing sea ice forecasting and marine forecasting and sea ice forecasting. And that has been going on for several years, totally independently of our work as well. So the people are doing. There's lots of projects going on across Canada for sure. But that is much more. It seems to be a bit more regionally focused, but I don't know enough about it. And it's been really successful. It's a different kind of. I talked about different prediction systems. It's a different one for various reasons that I can't go into right now. But it's a really interesting project. Yeah.
Okay.
Sure. Wow.
I think so.
Okay.
Okay,
Thanks
thank
for all the
you.
questions.
Let's applaud our speaker.
Thank you.
Okay. It's marvelous. So important that you're doing this. I think we ought to pass the hat and collect something for your research.
No. I don't think I would make it that direct appeal, but if you get a chance to talk to anybody in the know, I'd like to.
Well, I don't, unfortunately.
Yeah.
And when I do, I talk about nuclear weapons.
Well, there you go.
know?
Yeah.
We all have our thing.
That's important too. Yes.
My thing is nuclear weapons.
It's important to focus.
Yeah. Okay, it's really great of you. Thank you very, very, very much.
Thank you.
Appreciate
I really
it.
appreciate the interest.
And next week, by the way, usually we go out for supper or for beer or something after these events. But I just think it's so awful out there. I had to take a taxi instead of trying to drive, and I think we shouldn't try it tonight, fellas.
I think
You know, I'm sorry about that.
No, that's okay. That's
And
just fine.
so next time we will have our regular after lecture supper and beer. And next time will be a lecture by Professor Timothy Donay about Canadian peacekeeping. And Timothy Donay is he's the director of the program in global studies or something like that title at Wilfrid Laurier University. And it's, of course, very similar to the kinds of work that, well, many of the topics that we have in this lecture series and that we're all so deeply concerned about. So he's going to be talking to us about the Canadian peacekeeping efforts, which, unfortunately, Canada used to be famous for peacekeeping. People took a lot of pride in our record as peacekeepers, but that has been very much diminished in recent years. And he'll give us some thoughts about that. So thank you all for coming. I'm impressed that this many people managed to get here tonight, and I hope to see you next week. If you want to see one of the programs for the rest of the term, I mean, what's coming up before April, help yourself to some of the sheets here and Peace magazines and whatever else you see there that might look like fun. Thank you again, Paul.
Thank you.
Thank you.
I'm actually interested in that talk you were mentioning.
Oh, yeah, right. Yes. Yeah, I just needed to look at it.